Okay, Assalamualaikum warahmatullahi wabarakatuh. Hello everybody. Today we are from group 2. My name is Yusuf Setyanto and my friends Unzil Maughfiroh Firdausi will present about absolute value and real line. This is our material. First is the definition 2.1. The absolute value of a real number A denoted by absolute value A is defined by A if A greater than 0, 0 if A equals 0, and negative A if A is less than 0. For example, the absolute value of 5 equals 5, and the absolute value of negative 8 equals 8. Okay, you can see from the definition that if the absolute value of A greater than equals 0 for all A elements of R or real number sets, and that the absolute value of A equals 0 if and only if A equals 0. Also, the absolute value of negative A equals absolute value of A for all A, the elements of real number sets. Some additional properties are as follows. Okay, theorem 2.2.2. The first theorem, the absolute value of AB equals the absolute value of A times the absolute value of B for all A and B, the elements of real number sets. The proof is if either A or B is 0, then both sides are equal to 0. There are four other cases to consider. If A greater than 0, B greater than 0, then AB greater than 0. So that the absolute value of AB equals the absolute value of A, the absolute value of B. If A greater than 0, B greater than 0, then AB greater than 0. So that the absolute value of AB equals negative AB equals A negative B equals absolute value of A, absolute value of B. The remaining cases are treated similarly. The second theorem, the next theorem, the absolute value of A squared equal A squared for all A elements of R. The proof is since A squared greater than equals 0, we have A squared equals the absolute value of A squared equals the absolute value of A times A and equals the absolute value of A times the absolute value of A. Hence, it equals to the absolute value of A squared. Next, if C greater than 0, greater than equals 0, then the absolute value of A is less than equals C. If and only if negative C less than equals A less than equals C. The proof is as follows. If the absolute value of A less than equals C, then we have both A less than equals C and negative A less than equals C, which is equivalent to negative C less than equals A less than equals C. Conversely, if negative C less than equals A less than equals C, then we have both A less than equals C and negative A less than equals C. So that the absolute value of A is less than equals C. Okay, then the last theorem is the negative of absolute value of A is less than equals A less than equals the absolute value of A for all A is element of real number set. Okay, we can the proof is we can take C equal absolute value of A in part C before. So we can get the theorem like that. Okay, then the next is triangle inequality. It is saying that if A and B is the element of real number sets, then the absolute value of A plus B is less than equals the absolute value of A plus the absolute value of B. The proof is from the proof before in 2.2.2 part D, we have the negative of absolute value of A is less than equals A less than equals absolute value of A, and negative absolute value of B less than equals B less than equals absolute value of B. On adding these inequalities, we can obtain negative absolute value of A plus absolute value of B less than equals A plus B less than equals absolute value of A plus absolute value of B. Hence, from 2.2.2 part C, we have the absolute value of A plus B less than equals absolute value of A plus absolute value of B. Okay, 2.2.4 corollary. If A and B is element of R or real number sets, then we have two theorem here. The absolute value of the absolute value A minus absolute value of B is less than equals the absolute value of A minus B. And then the absolute value of A minus B is less than the absolute value of A plus the absolute value of B. The proof is we can see here, we can write A equals A minus B plus B, and then apply the triangle inequality to get the absolute value of A equals the absolute value of A minus B plus B less than equals the absolute value of A minus B plus the absolute value of B. Now, we subtract the absolute value of B to get the absolute value of A minus the absolute value of B less than equals the absolute value of A minus B. Similarly, from the absolute value of B equals the absolute value of B minus A plus A less than equals the absolute value of B minus A plus the absolute value of A. We can obtain minus the absolute value, the negative absolute value of A minus B equals negative absolute value of B minus A less than equals absolute value of A minus absolute value of B. Okay, if we combine these two inequalities using 2.2.2c, we get inequality in A. Okay, replace B in the triangle inequality by minus B to get absolute value of A minus B less than equals the absolute value of A plus the absolute value of minus B. Since the absolute value of negative B equals the absolute value of B, we obtain the inequality in B. Straightforward application of mathematical induction extends the triangle inequality for any finite number of elements of real number sets. Okay, next, if A1, A2 until and so on until AN are any real numbers, then the absolute value of A1, A1 plus A2 plus A3 and so on until plus AN, or the sum of A1 until AN is less than equals the absolute value of A1 plus the absolute value of A2, and so on until plus the absolute value of AN. These following examples illustrate how the properties of absolute value can be used. Okay, 2.2.6 is the examples. The first example is determine the set A of X elements of real number sets such that the absolute value of 2x plus 3 less than 7. Okay, from a notification of 2.2.c for the case of strict inequality, we see that x is element of A if and only if minus 7 or negative 7 less than 2x plus 3 less than 7, which is satisfied if and only if minus 10 less than 2x less than 4. Dividing by 2, we conclude that A is equal to X is the elements of R where negative 5 less than X less than 2.
Okay, for the next example, determine the set B is defined as a set X element real number set for the absolute value of X minus 1 less than the absolute value of X, based on the fact that A less than B if and only if A square less than B square when both A greater than or equal 0 and B greater than or equal 0. We can see at the 2.2.13 in part A at the group 1 before. Thus, the inequality of the absolute value X minus 1 less than the absolute value of X is equivalent to inequality of the absolute value of X minus 1 square less than the absolute value of X. The absolute value of A square equals A square for any A by 2.2.2 in part B. We can expand the square to obtain X square minus 2X plus 1 less than X square, which simplifies to X greater than 1 over 2. Thus, we again find that P equals a set of X element real number set for X greater than 1 over 2. That method of squaring can sometimes be used to advantage, but often a case analysis cannot be avoided when dealing with absolute values. A graphical view of the inequality is obtained by sketching the graphs of y equals the absolute value of x and y equals the absolute value of x minus 1, and interpreting the inequality of the absolute value of x minus 1 less than the absolute value of x to mean that the graph of y equals the absolute value of x minus 1 lies underneath the graph of y equals the absolute value of x. We can see in this figure 2.2.1 for the absolute value of x minus 1 less than the absolute value of x. Next example, solve inequality of the absolute value of 2x minus 1 less than or equal x plus 1. There are two cases to consider. If x less than or equal 1 over 2, then the absolute value of 2x minus 1 equals negative 2x plus 1, and the inequality becomes negative 2x plus 1 less than or equals x plus 1, which is x greater than or equal 0. This case 1 gives us 0 less than or equal x less than or equal 1 over 2. For case 2, we assume that x greater than or equal 1 over 2, which gives us the inequality 2x minus 1 less than or equal x plus 1, or x less than or equal to. Since x greater than or equals 1 over 2, we obtain 1 over 2 less than or equals x less than or equals 2. Combining the two cases, we get 0 less than or equal x less than or equal 2. We can see the figure 2.2.2. Here, the figure of 2.2.24, the example for the absolute value 2x minus 1 less than or equals x plus 1. Okay, next example. Let the function f be defined by fx is defined by 2x squared plus 3x plus 1 over 2x minus 1 for x greater than or equals 2 and x less than or equals 3. Find a constant m such that the absolute value of fx less than or equals m for all x satisfying x greater than or equals 2 and x less than or equals 3. We consider separately the numerator and the denominator of the absolute value of x of fx equals the absolute value of 2x squared plus 3x plus 1 over the absolute value of 2x minus 1. From the triangle inequality, we obtain the absolute value of 2x squared plus 3x plus 1 less than or equals 2 times the absolute value of x squared plus 3 times the absolute value of x plus 1 less than or equals 2 times 3 squared plus 3 times 3 plus 1 equals 28. Since the absolute value of x less than or equals 3 for the x under consideration. Also, the absolute value of 2x minus 1 greater than or equals 2 times the absolute value of x minus 1 greater than or equals 2 times 2 minus 1 equals 3. Since the absolute value of x greater than or equals 2 for the x under consideration. Thus, 1 over the absolute value of 2x minus 1 less than or equals 1 over 3. For x greater than or equals 2. Therefore, for x greater than or equals 2 and x less than or equals 3, we have the absolute value of fx equals 28 over 3. Hence, we can take m equals 28 over 3. Note that we have found one such constant m. Evidently, any number h greater than 28 over 3 will also satisfy the absolute value of fx less than or equals h. It is also possible that 28 over 3 is not the smallest possible choice for m. Okay, next topic is about the real line. A convenient and familiar geometric interpretation of the real number system is the real line. In this interpretation, the absolute value of an element A in the real number set is regarded as the distance from A to the origin 0. More generally, the distance between elements A and B in the real number set is. We can see in this figure 2.2.3. The distance between A equals -2 and B equals 3. We can get the distance is 5. Later, we will need precise language to discuss the notion of one real number being close to another. If A is a given real number, Then saying that a real number x is close to A should mean that the distance between x and A is small. A context in which this idea can be discussed is provided by the terminology of neighborhoods, which we now define. For the 2.2.7 about definition, let A element in the real number set and epsilon greater than 0, then the epsilon neighborhood of A is set. For phi, epsilon of A is defined by a set X element in real number set for the absolute value X minus A less than epsilon. For A element in real number set, the statement that X belongs to phi epsilon of A is equivalent to either of the statements. We can see at the figure 2.2.4 about an epsilon neighborhood of A. Next, 2.2.8 about theorem. Let A element in the real number set if belongs to the neighborhood phi epsilon of A for every epsilon greater than 0, then X equals A. For the proving, if a particular X satisfies the absolute value X minus A less than epsilon for every epsilon greater than 0, then it follows from 2.2.9 at the topic before in group 1 that the absolute value of X minus A equals 0, and hence X equals A. For 2.2.9, for examples, the first example, let U is defined by a set for X, which is X greater than or equals 0 and X less than or equals 1. If A element in U, then let epsilon be the smaller of the two numbers A and 1 minus A. Then it is an exercise to show that phi epsilon of A is contained in U. Thus, each element of U has some epsilon neighborhood of it contained in U. For next example, if I is defined by a set for X, which is X greater than equals 0 and X less than or equals 1, then for any epsilon greater than 0, the epsilon neighborhood for phi epsilon for 0 contains points not in I. And so phi element of 0 is not contained in I. For example, the number X of A is defined by negative epsilon over 2 is in phi epsilon of 0, but not in I. Next example, if the absolute value of X minus A less than epsilon and the absolute value of Y minus B less than epsilon, then the triangle inequality implies that the absolute value of X plus Y minus A plus B equals the absolute value of X minus A plus Y minus B. We get the absolute value of X plus Y minus A plus B less than or equals the absolute value of X minus A plus the absolute value of Y minus B less than 2 epsilon. Thus, if X, Y belong to the epsilon neighborhoods of A, B respectively, then X plus Y belongs to the 2 epsilon neighborhood of A plus B, but not necessarily to the epsilon neighborhood of A plus B. Okay, that's all for our group. We hope this presentation is very useful for you. Thanks for watching. Wassalamualaikum warahmatullahi wabarakatuh.